Kamaraj College of Engineering and Technology, affiliated with Anna University. With nearly 2 decades of experience in both academia and industry, Dr. Ramesh has served as an assistant professor for several years and also worked as a software engineer at Computer Science Corporation, Chennai. This unique combination of teaching and industry exposure enriches his lessons with both theoretical depth and practical insight. His areas of expertise include communication theory, wireless and mobile communication, circuit theory and analysis, MIMO systems and 5G technologies, embedded and real-time systems. Dr. Ramesh has published numerous research papers in reputed international journals and IEEE sponsors conference. His doctoral research focused on the design and performance analysis of novel four-port MIMO antennas for automotive communication system. He has consistently produced excellent academic research, often achieved above 90 percentage in the courses he handles. In addition to teaching and research, he has actively contributed to the academic and administration, curriculum development, placement coordination, and NBA activities. He has also served as a resource person in the faculty development program and has completed certifications such as Cambridge Business English Certificate and NPTEL Elite courses. He is known for his dedication, leadership qualities, and commitment to academic excellence. On behalf of ECE, PSN College of Engineering Technology, I extend a warm welcome to today's resource person, Dr. M. Ramesh. We look forward to gaining valuable insights from his expertise. Thank you, sir. Now, welcome you, sir, to the presentation.
Thank you, madam. Good morning to the participants. Now I am here to discuss on the topic design challenges in antenna design for next generation wireless communications. In that, specifically, I'll be discussing with one work which I have done, where I have done miniaturization with respect to the existing antenna. So my presentation outline will be, I'll be starting with introduction, where I'll be discussing wireless communications and massive MIMO, followed by the various generations and expectations of wireless networks. And I'll be discussing about the introduction to massive MIMO and its potentials. Then following that introduction, I'll be discussing about the parameters and factors which will be deciding the performance of MIMO antennas. Then I'll be discussing the various challenges and problems that will be coming during the implementation of 5G and MIMO antennas. And in that challenges, specifically, I will be taking miniaturization because in today's session, I am taking one particular challenge, which is miniaturization, for which I have a work which is done during the research of my career. So I'll be discussing about the miniaturization, which I have done in the one of the works of my antenna design. And specifically, I'll be discussing about the novel four-port antenna NFPA, where I have implemented the miniaturization. So coming to the introduction, wireless communication, as we all know, the transfer of information between two entities is the integral part of any communication systems, and that communication systems channel can be either wired or wireless. And in case of wireless technology, we will be using electromagnetics or radio signals to transmit and receive information over the wireless channel. And this wireless technology is very important in any modern communication system because it is going to play a major role. It is going to decide the performance of the communication system. So wireless technology, it is completely dependent on the communicating devices like antennas, and that particular antennas will be converting electrical signal into electromagnetic signals in the transmitting side, and in the reverse category, it will be converting our electromagnetic signal into electrical signal in the receiver side. So we can have different types of antennas, and that can be designed according to the applications and the requirement which we need. So coming to the massive MIMO, actually MIMO refers to multiple input and multiple output. So massive MIMO, it is also known as large scale antenna systems, very large MIMO or hyper MIMO, or it can be called as full dimension MIMO also. So in the recent research field, we are going to equip base stations with a very large number of antennas when compared to the previously considered systems. So those large number of antennas in the transmitter as well as in the receiver is going to constitute the massive MIMO system. So this diagram shows the block diagram of MIMO, where we will be having m number of transmitting antennas and n number of receiving antennas. So between each and every transmitter receiver antenna pair, we will be having a fading channel path. For example, HNM represents the fading path between the nth receiving antenna and the mth transmitting antenna. So these transmitting antennas, receiving antennas, and fading channel coefficients will contribute the transmission and reception quality of the signal which we are going to have. So in the matrix forms, we can have H112, H1M in the first row of the channel matrix, and it will be ending like HN12, HNM in the last row of our channel matrix. So our design challenge in the wireless communication system can be based on this channel matrix fixing also. So this diagram shows the two transmitting and two receiving multiple input, multiple output system. So if you consider this one, we are having X1 and X2 as the transmitting antenna and Y1 and Y2 as the receiving antenna. So for each and every transmit and receive pair antennas, we will be having a fading channel path. For example, between transmitter X1 antenna and receiver antenna Y2, we are having the fading coefficient concept called H21. Okay. Sorry, any doubts or queries? Okay, madam, can I proceed, ma'am? Can you hear me, ma'am?
No doubt, sir. You can continue, sir.
Yes, sir, you can proceed, sir.
Okay, thank you, madam. So we can write the received signal Y1 and Y2 in the receiver side in terms of the transmitting signals X1 and X2 from the transmitter antennas along with the fading coefficients H11 and H12, H21 and H22. So in general, we can represent that transmitter receiver signal relation in terms of in the terms of matrix format as y is equal to hx into n, where this n is representing the noise, additive white Gaussian noise in most of the cases. So coming to the need for massive MIMO, so as per the data given by the cellular network service providers, currently there are 30 to 35 billion connected IoT devices along the worldwide. And because of this, we have tremendous increase in the data traffic. So that is why we are dealing with the three important 3D terms, which are device data and data transfer rate. Since we have 30 to 30 billion connected devices, we will be having definitely we will be having tremendous data which need to be transmitted, and at the same time that data should be transferred in a higher rate also. So this increase in 3Ds encourages the development of 5G and 6G networks. So coming to the generations of wireless networks, as we all know, in the first generation of networks, which was introduced in the year 1980s, the most important feature that was analog signals were only used for the voice communications, and it is of having less security. That is why slowly we moved on to the second generation of wireless networks, where uh, along with the analog signals, we are able to use digital signals for the voice communication, and along with the voice communication, we are able to have the text messaging as well. And in the second generation of wireless networks, we had the limitation of very less support for the internet. So again, slowly we moved on to the third generation of wireless networks. It was started during the year 1998. So in the third generation of wireless networks, we had the wireless communication along with the wireless mobile and fixed internet access, video calls, and mobile television. So again, in the third generation, we were having less support for the high speed internet when compared to the second generation. Even though we had internet access, we are having less support for the high speed internet. And slowly we were moving on to the fourth generation of wireless networks. It got started in the year 2008 to 2009, where we were able to have the data rates in the signal transmitted around the range of megabits per second. But again, during the fourth generation of wireless networks, we had lot of connected devices. So at that time, fourth generation wireless networks were had a difficulty to support that 50 billion connected devices. And finally, we are currently in the fifth generation and sixth generation. In the fifth generation, we were able to achieve ultra high data rates in the rate of 10 to 20 gigabits per second. We were able to achieve very low latency, and we had massive device connectivity, which can support up to 1 million devices per kilometer square. And in addition to that, we had so many wireless technologies options which were contributing for the performance improvement of the 5G and 6G networks. And even though we had a lot of improvement in the fifth generation wireless networks, we had some limitations, which were like it requires high power consumption, high infrastructure cost, device compatibility, security and privacy concerns. So requires uh, dense small deployment. So these are some of the disadvantages or limitations which were there in the fifth generation, and still research is going on to improve these limitations as a positive one. So when coming to the fifth generation and sixth generation networks, we are having we what are the expectations? It is like we should be having the wireless connectivity at all the times. Okay, so these are some of the expectations that we need to achieve in the fifth generation and sixth generation wireless networks. So some of them are higher user data rates, higher area throughput, great scalability in number of connected devices, higher reliability and lower latency, better coverage with more uniform user rates, and improved energy efficiency. So these are some of the metrics that should be improved in 5G. So all these metrics are conflicting ones. It is impossible for us to maximize all the metrics simultaneously. So definitely we will be going for a trade-off between the metrics. So according to the applications and the requirements, we will be going with which particular metrics should be improved. So accordingly, we will go with the design and deployment of the networks. So the best example that we can say is, if we want to increase the data rate in a particular application, definitely the throughput may go down, because when we increase the data rate, the number of bits which will be getting affected or which will be getting errored may be increasing, and because of that, throughput may go down. So if that is the case, two metrics cannot be, it is like two metrics cannot be simultaneously improved, so maximized. So in such cases, we can go with the trade-off between those two metrics. So massive MIMO, coming to the massive MIMO potential, we already know that MIMO refers to multiple input and multiple output. Massive MIMO refers to hundreds of antennas will be there in the transmitter and receiver. So we are going to see about the potentials which can be achieved in the massive MIMO.
சொல்லுங்க சரி சார் ஒரு சின்ன ஹெல்ப் சொல்லுங்க என்ன
So massive MIMO can increase the capacity of the system by 10 times or more. It can increase the data rate because we are going to use more number of antennas in the transmitter as well as in the receiver side. And so independent data streams can be sent out and the terminals can be served simultaneously. So in such cases, each and every transmitting antenna can send unique data so that our data rate will be increasing. The third important potential of our massive MIMO is it can be built with inexpensive low power components. Actually, in the olden days or in the existing system, we are having expensive high power amplifiers, but that can be replaced by many low power amplifiers with power range in the milliwatt. Again, the fourth massive MIMO potential, it can reduce the interference because we can have the beamforming. So those kind of things can reduce the interference also. It improves the energy efficiency because we are going to use low power signals and low cost as well as low power equipments only. And it enables the significant reduction of latency on the air interface, and it increases the robustness to intentional jamming. So these are some of the parameters or factors which are deciding the performance of MIMO system. So throughput of the system, how many bits are actually transmitted from the transmitter and how many bits are successfully received. So that decides the throughput of the system. Then modulation formats at the physical layer, antenna arrays and pattern in the base station, beamforming of the signals, scheduling of active antennas and data transmission, diversity reception. So out of these parameters and factors, I am going to take an example from the antenna design in which we will be having miniaturization. So in the work which I am going to present, I'll be taking these antenna metrics as the parameters. So those parameters are scattering parameters, envelope correlation coefficient, adaptive diversity gain, effective diversity gain, mean effective gain. So in addition to these metrics, we are having many more metrics that can also be evaluated with respect to the designed antenna. So coming to the S parameters, as we all know, it represents the scattering parameters. From that, we can fix the how much isolation is achieved, how much return loss is achieved. So those things can be analyzed in terms of scattering parameters. So coming to the envelope correlation coefficient, it depends on the field quantities of the ith and jth antenna. So we will be having Fi represents the field quantity from the ith antenna, whereas field quantity from the jth antenna will be represented by J. So this envelope correlation coefficient represents how much correlation is present between the radiation occurring between the various MIMO elements. We will be having, for example, we are having two MIMO elements, two transmitter MIMO antennas now. Those two antennas will be emitting radiations, and how much correlation between the radiation between those emitted signals, that is going to decide the envelope correlation coefficient. So next parameters are diversity gain, where we will be having adaptive diversity gain and effective diversity gain. So this is the formula. So adaptive diversity gain will be depending on the envelope correlation coefficient. So that is equal to 10 into square root of 1 minus ECC square. That is the adaptive diversity gain. Whereas effective diversity gain, it depends on the adaptive diversity gain multiplied by the total efficiency. And mean effective gain, finally, it represents the gain achieved in the total system, which will be depending on the cross polarization ratio along with the gain of the antenna and the power of the signals transmitted and transmitted. So what are the challenges and the problems in the implementation of 5G, 6G and MIMO antennas? So development of new architectures is a major concern in 5G and 6G networks. There is need for handling other implementation issues in the context of users, example interference removal, handoff management, QoS guarantee, channel accessing, and in the context of infrastructures, it is load balancing. So there are several ongoing research works which will be dealing with these challenges. So some of the techniques are full duplex radios, dense deployment techniques, millimeter wave technology, massive MIMO, and visible light communication. So these techniques definitely will be helping us to satisfy the 3D demand. So due to the higher data rates, spectral efficiency, latency, cost, and channel capacity demand for an advanced communication system, lower frequencies of 5G, new radio sub 6 GHz have already been utilized for larger area of coverage in the present time. So hence definitely there is a need for new technology and new techniques which will be used for the development stage of other applications which require gigabits per second data speeds. So many countries already have used the spectrum as per their requirement. So the modern communication system requirement of both wide bandwidth as well as high gain are covered by using ultra wideband technology that plays a vital role in the wireless communication. However, ultra wideband technology is mainly affected by multipath padding degradation in cable-free communication. So one of the solution for the multipath fading is going to be the use of MIMO and the MIMO antenna, which will enhance the capabilities of the wireless communication system. So under the roof of massive MIMO, we are having various implementation research areas which will be covering novel modulation scheme, multiplexing, beamforming, throughput maximization, antenna placements, could be efficiently designed to maximize the performance metrics. So the most challenging task in the MIMO is the isolation between the multiple antennas while achieving the connected ground structure. So there are various techniques which are already available, which are decoupling steps. Steps can be introduced between the multiple elements of the MIMO antenna. We can have the defected ground structure, EBG, that is electronic band gap structure. We can use a split ring resonator. So these things will be definitely improve the isolation between the antennas in the MIMO. And for implementing MIMO antenna with wide bandwidth, different techniques are proposed, like slot and micro strip fed, 4 steep lines incorporated, modified rectangle along with the corners, a dipole with a ground having V-shaped branch. So these are all some of the works which are already there in the literature. And in addition to that, there are a lot many research gaps are still there to to face the or to compensate the challenges in the implementation of massive MIMO. So what is the motivation behind the MIMO antennas design? Various MIMO antennas have very big sizes due to improper utilization of the substrate space. The wideband MIMO antennas are limited for portable applications, and all the influencing parameters are not discussed in detail in the existing designs. There are so many antennas with separate radiating elements, but common ground elements will be there. Ground antenna elements will be there. So which are very few due to lack of impedance matching and isolation enhancement approaches. Finally, most of the MIMO antennas are based on the planar structure, and very few designs are for fractal MIMO antenna available. So with regard to the research work which I am going to show, we are going to have 1 minute. So in this presentation, I'm going to tell about one 4-port MIMO antenna operating at 2.45 gigahertz, which can be specifically used for the automotive communications. And in this 4-port MIMO antenna, I have achieved miniaturization geometry by introducing structural modifications in the existing reference antenna. So a 4-port miniaturized MIMO antenna is constructed, and the proposed MIMO antenna is found to exhibit good impedance and radiation characteristics. The combined radiation pattern of the antenna is tested and inferred that MIMO antenna offers omnidirectional coverage along the azimuth plane. Along with this radiation pattern and antenna impedance characteristics, I have tested the ECC, ADG, EDG, and MEG. So ECC represents envelope correlation coefficient, ADG represents adaptive diversity gain, EDG represents effective diversity gain, and MEG represents mean effective gain. So these are evaluated for the designed antenna, and the MIMO metrics are found that it is well within the accepted limit. And finally, the onboard performance of the proposed 4-port antenna is studied using the 3D electromagnetic solvers. So for all those, I'm having the diagram which will be showing how that particular metrics are achieved. So as already mentioned, this is going to be the proposed antenna. This is one element of the 4-port MIMO antenna. So if you see this diagram, you are having two parts, two sections. One represents the front view and the other represents the rear view. In the front view, if you see, you will be having circular slot, and in the rear side, you will be having one arc-shaped feed line. Okay, so we will be having middle substrate. On both sides of the substrate, we are having elements which are connected, which are placed so that it is going to perform very well in terms of radiation and the other parameters. So how I have achieved the major aim of this proposed antenna is to reduce the operating frequency of 2.45 gigahertz without increasing the footprint. In this diagram, for this one element, I'm going to have operating frequency at 2.45 gigahertz. This figure shows the reference antenna from which how I have done the structural modifications, and because of that structural modifications, how the operating frequency is shifted from 4.5 gigahertz of existing reference antenna to the 2.45 of 2.45 of proposed antenna. So in the figure A, 2A, if you see, you are having one square shaped sectoral in which you will be having a arc shaped slot at one side. In the other side, you will be having a arc shaped feed line. From that, I am going to make the structural modifications. That structural modification will be like, in the front side, instead of having a arc shaped slot, I am going to have a circular slot. This circular slot will be having in the front side, and in the rear side we will be having one same sectoral arc shaped slot. This arc shaped slot in the rear side will be used for feeding the signal into the antenna. So in this diagram you can see how the reflection coefficient is there for the reference antenna as well as for the proposed antenna. So for the reference antenna, we can see that the reflection coefficient is at around 4.4 gigahertz, whereas for the proposed antenna, we are having reduction in the operating frequency, which is there in the 2.4 gigahertz. This 2.4 gigahertz can be used for the ISM band application, that is industrial, scientific, and medicinal applications. So this diagram shows how the value of R can be changed, so that because of that, the reflection coefficient will be distributed for different frequencies. So here you can mention that this R represents, capital R represents the radius of the circular slot. This detail shows the optimized dimension of the proposed antenna. This capital L and capital R represents the length and radius of the front view side of the proposed antenna, and small l and small w represents length and width of the feed line. Then R1 and R2 represents radius, inner and outer radius of the slot, that is feed line slot. Whereas this R3 and R4 represents radius of the circular slot. So this is the 4-port MIMO structure. I have designed one element of the MIMO antenna, MIMO system, and 4 such elements are combined together, and because of that, it will be acting as a MIMO element. So here, port 1, port 2, port 3, and port 4 represents feeding point of the various MIMO elements. Again, front view as well as the rear view of the 4-port MIMO antenna is displayed. So this diagram shows the reflection coefficient or scattering parameters for the simulated and the measured antennas, measured reflection coefficient characteristics of the 4-port MIMO antenna. So when respect to the with respect to the simulated and measured reflection coefficient, we can see that there is slight deviation in terms of reflection coefficient parameters. That may be because of the SME connectors which are introduced for feeding the data or feeding the signal into the MIMO antenna. This diagram shows the radiation pattern of the proposed MIMO antenna measured from port 1, port 2, port 3, and port 4 separately. So from this we can infer that these 4-port MIMO antennas can individually transmit the data in an omnidirectional way. So this is the radiation pattern measurement setup for the 4-port MIMO antenna design. This diagram shows the simulated and measured radiation pattern for the 4-port present in the MIMO antenna. That is port 1, port 2, port 3 and port 4. From this we can infer that our antenna is able to radiate signals in an omnidirectional way, and this diagram shows the simulated and measured gain characteristics and the simulated efficiency characteristics. From this we can see that gain of the simulated simulation results and the fabricated measurements is having small deviation because of the SME connectors which were introduced in the feeding point of our antenna. So far what we have seen is how we need to how we are going to achieve the frequency reduction when compared to the existing antenna in the proposed antenna. That frequency reduction actually will increase the footprint of the antenna, but without increasing the footprint, how we are going to achieve the frequency reduction? Because we all know that our lambda value will be inversely proportional to the frequency of the antenna. So if we want to have the frequency reduction, definitely lambda value will be increasing, and in turn our antenna footprint will be increasing. But in this designed 4-port antenna, because of the structural modification in the existing antenna, we are going to achieve frequency reduction without increasing the footprint of the antenna. Because in the existing reference antenna, the footprint is 15 cross 15 mm square. In our proposed antenna also, the total footprint is 15 cross 15 mm square only. But our operating frequency is reduced from 4.4 gigahertz to 2.4 gigahertz without increase in the footprint. That is the major conclusion, major inference that we need to take, but not at the compensation of performance parameters of our antenna. So this blue color line represents the antenna which is taken as a reference, and this circular slat antenna represents the proposed antenna. So if you compare both the antennas, both are having the same footprint. For one element, it is going to be 15 cross 15 mm square. So 4 such 15 cross 15 mm square antennas are measured together, and it is going to act as a MIMO antenna. And for that MIMO antenna, how the performance parameters are there, that one we have evaluated. So coming to the measured MIMO metrics at 2.4 gigahertz using far field data, I am going to take one port as a reference, and by using that port as reference, I will be feeding one port, and how much radiation is occurring in the other antennas or other ports, that is measured in this particular in this table. Okay, so in this also, in the research work, cross polarization is taken as 0 dB and 1 dB and 5 dB for isotropic urban and semi-urban areas. So this 0 dB, 1 dB and 5 dB are taken as a random one for the different vehicular scenarios, that is isotropic urban and semi-urban. We can check the performance parameter using the far field data for single isotropic area with different XPR values also. So from this table, we can infer that our antenna is having gain value and envelope correlation coefficient value well within the limits. So next one is going to be mean effective gain at 2.4 gigahertz. So it is the ratio when compared to mean effective gain 1 with, in port 1 with respect to the other ports. That values are displayed here. So that values also are accepted ones And this diagram shows the onboard performance of the proposed MIMO antenna in the azimuth plane as well as in the elevation cut. So in both the things, we can infer that our antenna is able to radiate signals in the omnidirectional level, and it is accepted one. So comparison of the single element antenna with the state of the art, I have taken some reference papers, and from that reference papers, how this novel four-port antenna is having size reduction. So in this, if we see our antenna, our novel four-port antenna is having 100% size now. When compared to that size, how much size reduction is done for the other works which are reported in the literature. So if we see for the reference numbers 8, 9, 10, 11, 12 and 13, which are the literature works which are given, which are already there in the literature, size of the antenna is high when compared to our novel four-port antenna. So, but if we see the gain value 3.2 is there for our novel four-port antenna, which is an acceptable one. For example, in the reference number 10, if we see, even though in the reference number 10, we can see that not only the size, but also the gain is very less when compared to the proposed antenna, which we have given here. So from this, what we are inferring is we are having, when compared to the existing literature survey works, we are able to achieve more size reduction for the better placement of antennas. This one shows the 4x4 MIMO size reduction. Okay, when compared to our novel four-port antenna, which is having a total size in 0.25 cross 0.25, having a number of 4 elements, and it is going to act in the 2.45 gigahertz, and it is having 100% size now. When compared to that size, how much size reduction is achieved for the our work when compared to the existing survey works. So what is the inference from this proposed antenna is our proposed four-port novel four-port antenna is having reduced size, reduced footprint. That is, size reduction is achieved by reducing the frequency to 2.45 gigahertz from 4.5 gigahertz, even though there is no change in the footprint from the reference antenna. And again, our antenna is having the lowest profile. Our antenna is having gain which is greater than 3 dBi. Our antenna is having dual layer configuration. That is one of the unique feature of our antenna structure, because unlike other antennas which are presented in the research, they will be having a single layer configuration. In top layer only they will be having the antenna, and below that they will be having substrate. Whereas in our work we are having dual configuration, means we will be having substrate. On both sides of the substrate we will be able to have the antenna elements. So again, efficiency is better when compared to the existing works, and our antenna is having the highest packing density also, because our antenna is having dual layer configuration, and because of that we are having smaller footprint. So one thing we need to remember, our wavelength of the signal which is going to be transmitted, lambda, will be equal to velocity of the light divided by the frequency of the signal which we are going to use. So in such a case, if we increase the frequency, definitely our lambda value will be small. And if we decrease the frequency value, if we want to have the reduced frequency of transmission of the signal, we will be having, definitely will be having increased value of lambda. So in turn, because of the increase in lambda value, our antenna size will also be increasing. So the major novelty or major thing that we have achieved here is without any size reduction or size increase, we are able to achieve the frequency down from 4.5 to 2.4 gigahertz. So as mentioned, already mentioned, our ECC, ADG, EDG, MEG values are well within the acceptable limits. ECC is less than 0.2, which is accepted, and ADG, it's a gain value. It is close to 9.7 dB, and our effective diversity gain is almost equal to 8 dB. So these results indicate that this particular proposed MIMO antenna can be used for the vehicular IoT networks. So concluding this one, the design testing of 4-port antenna operating at 2.4 gigahertz has been done, and it is suitable for automotive IoT communication, because nowadays the world is moving around IoT. So definitely, if we are designing one antenna which is well suitable for the IoT communications, that will be well appreciated. So the circular slot antenna element with 4-port has a miniaturized geometry realized using structural modifications with the footprint of 15 cross 15 mm for the single antenna. The proposed novel 4-port antenna MIMO is found to reveal good impedance and radiation characteristics as well. So we are having other challenges as well. So in this presentation, mainly I have discussed about the miniaturization in the reference or existing antenna, and because of that miniaturization, we can achieve some of the requirements of our applications. So there are some other challenges also that can be considered for the research in while implementing the antenna design for the 5G and 6G wireless communication networks. So actually this is only for the 2.4 gigahertz application. So this can be extended for the terahertz application also, and we can go for the combined arrays also. And in this work, how that dimensions of the antennas were calculated, that is placed in a random order only. So that can be still modeled in a mathematical equations. And because of that, if you are introducing more different structural modifications, then it will be a good basic slot radiator achieving a perfect performance metric of our requirement. So these are some of the references I have taken. These are the references which are used for implementing the proposed antenna when compared to the reference antenna. So any questions?
Sir, can you say which type of software will be very suitable for 5G and 6G communication? I worked only in HFSs.
No, ma'am. There are lots of softwares
Sir,
which
I
are
want to know
available.
it should be open access, but we can take the all parameters. Like that, we can say one or two softwares.
No, ma'am. There are certain things that we need to consider, because when we go for higher frequency applications, definitely there will be like we need to simulate the things which we are doing in the design. So in such cases, if we go with the open source softwares now, that will be having the limitations of low frequency application. So if we go for high frequency applications, definitely if we go with licensed software which are having more minute mathematical mathematical modeling which are inbuilt with the simulation, that will be well and good. So as far as current trend for the design of antenna with higher frequency applications, either we can go with the computer simulation technology, or we can go with the high frequency structure simulator. There are certain other softwares which can be used for low frequency applications, but it is based on the application and the requirements which we have. When we go with the high future generation wireless networks, definitely the operating frequency will be high. So in such cases, definitely if we go with a software which is having more mathematical details, no, that will be well and good, ma'am.